Alrighty. Woo! Hello everybody, welcome back. We be continuing with this stuff. Okay, so we got our character body. Let's give it a shape, collision shape. And this is gonna be, I think a sphere actually will work okay. Okay. I think for the time being this will do. Now, I'm gonna program this. This is crawler large. And I can place it into the level, but I'm thinking maybe we should get a... Man, why are all the panels opening up on the second monitor? I'm not sure why. We can get a dev panel for spawning enemies. Dev tools. Okay. There we go. Let's get a panel container. Whoops. New child node. See, I don't know why, but it keeps popping up the window on the other monitor. Panel container. Let's give it a minimum width. And then VBox container inside. Let's get a label. Label's gonna say spawn enemy. And what do we do? Shall we just have it automatically create the list? Sure. Yeah. Let's get another VBox then. Enemy list. Okay. Let's make a enemy dict, enemy DB. And then we're going to say crawler large. And we're going to take the crawler large TSCN, place it right here. Now, we're going to create buttons, as many buttons as we need. They're going to go into this node here. So we're going to do for enemy key in enemy DB. What are we going to do? Well, we're going to do new button. Let's make a variable called new button. And then we're going to talk to button, make a new one. Well, hello there. Indeed. We're going to add child of this new button. Then the text of this new button is going to be enemy key. And we need to connect a signal. What signal? Button down. It is going to be connected to func spawn enemy. Enemy key is going to be passed along. So we're going to be creating a function, a callable object, to connect to this function here. We're going to bind an additional parameter, which is enemy key. So when we press on this button, using the button down signal, it's going to call this function in this object, so this script, and it will send an additional parameter of the key. Now, since we know the key, we know the enemy scene. So what we're going to do is spawn in a new enemy. So we're going to do so by loading the whatever enemy key we are getting from the enemy database. And then when we load it, we'll instantiate. There we go. Instantiate. Okay, give me 1 sec. I gotta open the door. Okay, so we got the new enemy, instantiated, loaded, instantiated, and now we need to place it in the level. Get tree, current scene, add child, new enemy. Now, we need to position it. Where do we position it? Well, we could position it where the player is looking at. You sound so energized. What were you doing break time? Guzzling down cups of coffee. Oh god. Okay. What do we got? We need to have the player. Okay, let's open up the player. We should have a raycast. Okay. It's kind of a long one. Okay. I may need to make another one. Or let's just use code. All right, let's do this. We're going to take this camera, copy node path. Does the player have a variable that contains this camera? I would imagine he does. No, FPS player. I don't think we do. There's a bunch of rays here. All right. Okay, fair enough. Let's go into the DevTools. Let's not waste time. Okay, so we need to cast a ray using the something something space in the editor. Okay. Let's look up. There we go. Let's look up any functions that have to do with raycasting, but that are not belonging to the raycast node. Physics server, rendering device, render server. Nope. Project settings. I need to be able to find this myself, so let's see it. It's not mesh. It's not occluder. It's not material texture. It's not a resource then. Maybe. Multi-mesh, navigation mesh, shape visual shader node. Subgizmos intersect ray. That's interesting. Physics. Okay, physics ray query parameter is something that you supply into the function that I'm looking for. It's intersect ray. Physics direct space state 3D. There we go. intersect ray, and we need to get the direct space. Okay, so if we can get the direct space 3D, I can hear your soul. I know. Why does my soul kind of sound like my brother for some reason? Let's see. Okay, so direct space, we have to get access to the direct space, but I believe to do so, we have to do get root. Jolt physics, direct space state 3D. Huh. Are we gonna have to use the jolt function? Okay. Let's try this. And then something to do with ray. Intersect ray. There we go. That's a method. Okay. Now, it wants a parameter. Parameter set containing physics ray query parameter 3D containing all the parameters. So var params physics. Okay, what the hell was it called? Physics ray query parameters 3D. Make a new one. Now, where do we start? From is going to be the player's camera. So player and then we have to go to the player, get the camera. Okay, pin line, flashlight. Can we get rid of all this stuff we don't need? Player. There we go. Copy. Copy, copy, copy note path. Flip switch. Nope, that's not what I need. DevTools. Come on. So get node. This is the node we're getting. That's from. We are going to have to talk to this a couple of times. So player cam. As a matter of fact, yeah. Okay, that's fine. Param from player cam global position. Okay, now params 2 is going to have to be where the camera is looking at. So global transform dot basis dot z times 20. Okay. Next. What else do we have that we need to set here? Yoo-hoo, any day now. Okay. Collide with areas, collide with bodies. Collision mask by default should be okay. We don't need to exclude anything. From to exclude. Okay. Collide with area set to false by default, body set to true, so we don't actually have to set that. Just from and to is okay. And then that's it. We just need to take the params, supply them here, and that's it. So, collision result. Let's print. Can I call non-static function intersect ray and class physics direct space state 3D directly make an instance instead? Which means we can't just do this. We have to talk specifically to the space state of our current level. So get tree, current scene. Get space state. Physics directs body space state. And then there's one here. There's world 2D and the world 3D. Get space state. Okay, so world 3D. How do we get the world 3D? Can we just talk to it? Not found GDScript native class. Direct space state. Interesting. That's a property. Okay. Is that going to work? Well, let's see. Should be able to see something right now. Let's make sure that we are working with a sandbox. Testing sandbox. Yeah, there we go. So, what's everybody up to? Evaluate set SP. Params. Whoa. Hey. I am talking to a completely incorrect thing. Okay. I lost it. What the hell are we doing? Watching you leave half codes in the and trying to run it. Yeah, it's common occurrence. I want to save. Okay. And then we're gonna crash apparently. Hello? Oh. Man, the freaking panel opens up on the side. There's actually like class for the raycast programs. The direct space state is the class. Okay, let me just double check this real quick. It wants intersect ray. It wants physics, query parameter 3D. That's what it wants. So that's why I messed up here. That's the parameters. Now here, I think that's basically it. Okay. Valgate direct space state on base world 3D. So I think we need to do get world something something. Unless it's get, yeah. Get world 3D. We call it on the node. Geez. 3 lowercase d. And I think calling it on this one should allow us... Huh. Not found on base self. Okay. Let's do get tree. Current scene. Get world 3D. A tentacle function intersect ray on base null instance on a null instance. Why are you calling it... Oh. Well, hold on a second. Why am I putting this stuff here? Whoops. I gotta do this here. Okay. All right. So that crashed. Still calling on a null instance. Intersect ray. Get world 3D. Returns the current world 3D resource this node 3D node is registered to. Okay. So it's a world 3D resource that has a parameter called direct space state. Which is correct. So maybe we're not getting the world. Worked. Beautiful. All right. It does give you the world. Okay. So what the shit? We have a world, but that world doesn't have a direct space state? Physics direct space state 3D. To get the direct space state from the physics server. Ah, so maybe it's different now. I think we've been down this road before. Space get direct state. Okay. Now you see, I haven't used this enough times to remember that. Space get I call expected one argument. Space ID. Okay. Returns the state of a space, a physics direct space state 3D. This object can be used to make collision intersection queries. Okay, well, how the flip do I know which space to give? Just 0? On like query parameter, you don't call it with new, but call it with create. It seems to work because I've done this before. Okay, let's say 0. Sure. Cannot pass a value of 0 because it wants a resource ID. Okay, let's find in files. Terrain get world 3D. Direct space state. And then tree cluster. Get world 3D dot direct space state dot intersect ray. It's right flipping here. We use it to place the trees. So what the okay. Function get world 3D not found itself. Now it kind of makes sense because that's a tree cluster which is placed into the level. This is dev tools, which is not in the level. It's a singleton. So we got to do get tree current scene get world 3D, which is, you know, us going right back to where we were before. But that's what we had to do. Intersect ray in base null instance on a null instance. Get world 3D. Maybe we'll do it on the player. Get tree, get root. Didn't have to do it there. But I'll try it. Oh, yeah. Apparently player doesn't exist in the world. Son of a gun. Hold on. Maybe the error is telling me something. Spawn enemy space state is inaccessible right now. Wait for iteration of physics process notifications. Son of a bitch. Okay, so we have to do call deferred. That's what. Okay. So, spawn enemy. Can I call this flags? Callable has to have a parameter to make it be deferred, right? At least the loading times are good. Call deferred. Okay, but we can't do that. Unless grab focus dot call deferred calls the method presented by this callable in the deferred mode. Okay. You know what? Cannot return value from call deferred because it's void. Right. Okay. Spawn enemy. This is positively the most retarded thing I've ever done, but okay. Method string name. Parameter variable. You could have a method that calls spawn enemy deferred, which is what I'm doing right now. But I feel like you have to have the ability. There's got to be a way to set callable. Yeah. Okay. Okay. It's a stupid, but okay. Would have been faster to just place another raycast in the player. But hey, look at that. Oh, holy shit, this thing is huge. Oh god. Okay, sure. Let's do that. That works. So now, we should have gotten something in the collision result. The thing is awesome. I know, right? It's looking fucking badass. Okay, now. This gave us a non-existent collision. So we're going to do if collision empty. So if the dictionary is empty, or I guess only if it's not empty, only then are we going to spawn the enemy. And we need to have some piece of data in there. Okay. Now this is a function empty. Right. Is empty. Oh, you sack of shit. Come on. You give Python and JavaScript people append and pushback. You don't give us empty and is empty? Okay. I think it used to be called empty in Godot 3. Not with object, just arrays. Oh boy. Okay, cool. So, it always gives us an empty result. But I bet if I look up, okay, the ray's coming out of the back of our head. So we gotta go Z negative z, or multiply by negative 20. Now let's do negative z, that's fine. So negative z multiplied by negative 20, and then what do we get? We get position, face index, collider ID, collider shape. That's cool. We don't need it though. New enemy dot global position equals, and then we do collision result and use position here. Cool. Let's give it a test. Man, this is pretty cool. Perfect. Okay, now that's not quite right though. Interesting. Okay, is it because it's local to the ray? Let me double check this. Intersect ray. Okay, apparently we're not allowed to control click on it. Intersect ray. Whoops, no. Get back. All right. The intersection point, you have to add from to the two parameters. Face index from starting point of the ray being queried for in global coordinates to ending point of the ray being queried in global coordinates. So I think it's just the fact that we gotta take the from. Wrong place. There we go. Params from. And add the position. Although I would expect that it would be... Nope. Okay. Yes, I don't think this is it. Maybe it's because we have to make sure we use the space state of the node within which we place it. Get world 3D. I mean, I'm pretty sure that the world 3D is the same for everybody. Oh, hold on. No, not really. It'll be horrifying when they're crawling after your ass. Oh, God. Okay, well, these things are lining up. By the way, they're lining up on the x-axis by the looks of it. Yeah, they're all looking down the same direction. Frizzy, sup? The sky's up. Hold on a second. I smell something burning. I think the neighbors are firing up the barbecues. Barbecues don't smell that way, by the way. They're definitely burning plastic or some shit. Also, that means we're gonna have a whole bunch of gypsy music in the background very soon. So that's gonna be until like 2 in the morning. Whew. Okay. Cool. What do we got here? Collision. Get tree current scene. Get world. Track space state. From. From where? Maybe it's... No, player cam. Global transform. Global position. Global transform that basis.z times 20. Let me try this. CSG Sphere 3D. New. Add child. SP. Do it. Do what? And then SP dot global position equals this. Double dare you. I dare you. Double dare. I have no idea what you motherfuckers are talking about. Okay. So that is correct. Or that is exactly where that's supposed to be. Maybe it's colliding with the player. What is it colliding with? CSG box. That makes sense, because that's the floor. Hmm. Okay, I'd really like to figure this out. I can always go into the player and use a add a raycast there, but I'd really like to figure out what the heck's happening here. Areas, falls, bodies, true, collision mask. Exclude. From to. We don't need to adjust any of these other settings. Okay, what other intersection methods do we have? Cast, collide, get, rest, intersect, point, ray, shape. Get censored here. Oh boy. Oh, get back. Okay. Params 2 is params from plus negative player count global basis. Okay. So let's double check that. Oh. Ah. Ah. It's not it. Although, did I do this right? From plus. Oh, hold on a second. Global position of what? This is supposed to be the global position. Oh, that's tree cluster. Can I? Okay. What do we do here? From, we did, oh, okay, we did global position here as well. So I think we got to do from and to global position. We got to go from player can global position to player can global position. I think that's what you meant. Plus this offset. Oh, which makes sense. Because the to parameter, I only gave it a direction. God damn it. Okay. Nice. As long as it's close enough. Yeah, that seems to work. Okay. Yeah, totally forgot to add the global position. Thank you. Perfect. All right, cool. So, now that we have this set up, we have the crawler large. What do we do with this now? Well, now we need to give it a navigation agent. Navigation link, navigation agent 3D. Experimental. Yay. Okay. And then navigation agent. After setting the target position properly, get next path position method must be used once every physics frame to update the internal path logic. So this is where we get into the whole, do we program this thing as a part of the enemy, or do we make it its own standalone thing? Let's give it a try. Let's give a standalone thing a try. NPC navigation. So we're going to give it a script of its own. Okay. Scripts, NPCs. Okay. And then var target position. What do we do here? So we have crawler. Crawler large has to have its own script. Ah, damn it. Go away. Vartar, that's right. Target position. So this is where we're telling it where to go. Now, I think the logic behind it is that this node doesn't talk to anything here. It is a completely self-sustained, self-sufficient node. We just give it data, and it will spew out whatever, right? So let's give it a function called set target position. But it already has a function called set target position. Doubling it up doesn't make sense. Let's go over here. Okay, let's make a var player scene. Make it false. Now, let's make it true for starters. And var target player. For now, we're gonna get tree current scene. I just need to get something up and running. We'll get tree, get first node in the group called local player group. But then again, it would have to have a vision cone of some sort of a system. So I guess just giving a raycast right away would make sense. And provided we never rotate the kinematic body, Might be able to work with it. Otherwise, gonna have to work with setting the raycast as top level, which makes it ignore the transforms of the parent. So, okay, let's do line of sight. Okay. We're going to give it visible. Top level. Okay, so that's going to prevent it from inheriting the transforms. Now, I'm going to do a node 3D. And then place the line of sight into it. We're going to do line of sight origin. And that's because we need to place the line of sight at this location at least. Okay, so let's make it equals to null. And then func physics process or just process. I think process is fine. So process. So we're gonna say line of sight global position is line of sight origin. Global position. So that should make it be in the same location. Next, there's only one player for the time being. So we're going to point to the player. So let's do, let's assume there's more than one player. So we'll do for x or for each player in get tree, get nodes in group, player group. Okay. And then I see we could technically work with space states again, but I think this will work out just fine. So we'll tell this node to look at target position. Target position. Each player dot global position. Okay, now that's going to make it always look at us, I think. Or not. Oh yeah, that's right. We have to do visible collision shapes. Maybe 20 is a little too lenient. Okay, so it's looking there. Interesting. Now, why is it looking there? Maybe this target position is in local space. Raise destination point relative to the raycast position. Right. Okay. Well, in that case, we're going to say global position minus, or it's player location minus global position, since it's relative. Now this will make the ray infinite. Also, before we do that, let me make this a much longer ray so we can spawn things a little bit further away. There we go. Now, this kind of means that it has an infinite look at length. So instead, what we're going to do is we're going to get line of sight global position direction 2 each player dot global position, and I suppose we can give it a variable called line of sight length, set it to 10. We're going to multiply this way. I think it might be wrong again because of the local space. Oh, actually, no. Look at that. 10's too small, though. Okay, let's do 30. $30 might be good. Ooh. Yeah, 30 seems a bit more reasonable. Okay. So, let's say target player becomes each player, and then we're going to break for the time being. So first player that it sees is the first player it's going to run for. We're going to figure out the logic for other players, like maybe have the other player store how many enemies are being targeted by them, or how many enemies target them. But we can set target player is null. Whoop, let's not break it. There we go. And then we go here. Okay. Now, we need a state machine. Okay. So if it's idle, then we pass for the time being. And then chase. Okay, so what does it mean that we chase? Well, we have the NPC navigation. Target position is going to be set to the target player dot global position. Okay. That's good. Now, I believe the NPC navigation, in this case, has target reached, navigation finished, link reached, waypoint reached. These are all really useful. But I suppose this is something that belongs in physics process. Because first of all, physics process doesn't run as often as regular process, and certain things just have to be available here. Okay. So if the player target, I guess we need to do if is not null, then we're going to set that as a target, and we need to now have some sort of a place to store simply the destination we're going to go to. Now this means that we're not programming this NPC navigation thing, so it's pretty useless. Okay. Destination point. So we're going to say if the player target is not null, we're going to set target position, and destination point is going to give us the next path position. Okay. Cool. In this case, we're going to say velocity is going to be set to global position dot direction to the destination point, and then move and slide is going to be executed as the last command like this. I'm going to set this to 20. Maybe we should pre-place one of them in the level. Okay. Well, it's not moving. And for the crawlers to take each other into account. Yeah, so they do have some sort of a obstacle avoidance. I have not been able to make it work. So that's something I'm going to have to figure out. NPC navigation dot get next path position, destination point, and then velocity, and then move and slide. All right, we never actually went to chase. Okay, right. I guess we can start by saying if it's idle, if, so we have a player scene variable. Player scene. Set it to true. You know, this part is for choosing the player to target. I guess we can say if player target is null, then this is where it's going to choose which player to target. Okay, but choosing a player to target... Well, no, that doesn't... If it is null, it hasn't been chosen yet. The first player that it sees, which we have yet to actually check if it sees it, that's going to be the player it will go for. So, line of sight, force raycast update. So get the collider. If collider is not null, then if collider is in group, player group, then it is indeed the player. Target player is set up, and then we break. Okay, now we need to be checking for, let's say else. What if the target player is not null? Well, then we will repeat this process. Okay, now the only difference is that the target player is what we're going to be looking at. I don't think we need to force it to be updated this case. We kind of have to do it here because we're running multiple consecutive raycast calls one after another. So we have to force it to update it one after another in the for loop. But here we're just doing one. So we get the collider, check if it's not null. If the collider is a part of the player group, player scene becomes true. Yep, otherwise player scene stays as false. Okay, now, if player scene is true, regardless of which state we're locating, we're currently in, state becomes chase. Now, I will want some sort of a transition, some sort of a preparation, like the enemy, stops, pauses, looks, turns, does a growl of some kind and then starts chasing. But for now, we'll just do this. Okay. Okay, now this is where I'm going to need to give it the ability to show me. Label 3D. Show me what the hell it's thinking. Okay. So I guess we can make it shaded. Make it billboard. Okay. Dev. Debug. And we're going to start by saying dev debug, I guess in the process function. Text is going to be, first of all, state. Have I baked the nav mesh? That's a very good point. Navigation region. I think navigation region is a little bit different now because the navigation region can just be sitting by itself. Geometry, mesh instances, root node, and children. Group by children. Static colliders both. And I believe that we could just have it done by group. Group explicit, group with children. So if I go here, do that. Nice. And then I can also go to this generator here. It's a static body, so I can give it a group. That should have technically accounted for it, unless I haven't saved. Of course I haven't saved. Beautiful. Cool. I wish there was some kind of a group that allowed us to exclude the top faces, but I don't think the navigation data is ever going to be using those faces. All right. That's good. Now it says it's idle. Okay, player seen is true. So player seen never changes. Okay. Player seen. Let's give it a take a look at here. Do you have game dev experience before Godot? Other engines. App Game Kit, Leadworks, GameMaker Studio. Just kind of looking around and experimenting. Aha, so PLC and assesses false. Okay, now it could be that it's just colliding with itself. No, it's not. Seems like it's smart enough to know that it's not supposed to be colliding with self. Okay. Let me maybe print it, see what it is that it's actually colliding with. Isn't group player group. Now, is our player in the player group? Or is he in the local player group? No, he's in the player group. So, print collider, print S. Let's see what it is that it's actually colliding with. Uh-huh. It's not printing at all. And we have debugger errors. Space state is inaccessible right now. Wait for iteration. What the heck? Oh, because we're running it in the physics process. God damn it, man. Come on. I guess we can't do that there. I'm going to have to do it in the physics process. Fair enough. It is technically physics related. I'm not too keen on running for loop logic in the physics process, but then again, we only have like so many players. And now it doesn't work at all. Do I have to force it? Let's try this. Let's try also printing target player. The name of the node. Nope. Base nil. Right. If null, we're gonna do this. Okay, so it does see me. Curiously enough, the raycast is not turning red. Huh. So player... Okay, let me try this. We're going to say plus none if target player is null. Else, it will use target player's name. There we go. That should make it less jumpy. Okay. Target player non-player. So it knows that I'm there. Oh, but we keep resetting it to null. Maybe we don't. Maybe target player starts as null. If it is null, we pick the first player that we see. And then we get the else statement. Yeah, that's very deceptive. The else never runs in that case, but the print commands and the label 3D get executed. Oh, okay, so we got the chase. Cool. And then it's always looking at us. Okay, we have movement. That's all that we really needed. That's good. Let me disable visible collision shape. So now we can do the crawl effect. Cool. It only took us an hour to set this whole thing up, but that is okay. I'm just going to pre-place one into the level. Crawler. Why is the script in the objects folder? Okay. So I'm thinking we should just continue using the direct space state solution when checking, where we're going to go here. Okay. So what do we need to do? Well, first of all, we need to know where's the raycast going to be shooting at. You see, we have all of these points. Oh yeah, the handle body one, by the way. I don't think the handle body is going to be a good way to control it. I think instead we're just going to have to directly address the body bone and then have its rotation be set this way. Because it technically works. If I do all this. And then go here, take the body, and then I can, rotate it and... Have you been a good boy? Have you been mauling people in the forest? Are you sure? Oh, we talked about this. Don't make me take out the baseball bat again. Oh, you like it? You like it, don't you? Okay. All right. So here's what we're gonna do. We know that these points are good starting locations. We know these points are good starting locations for us to run the raycasts. I'm more inspired than the one from Harry Potter. Hey, the one from Harry Potter is, My Little Pony in comparison to this. Right. So here's what I'm thinking. When the game starts, I'm going to sample the locations of these points, relative locations. They will act as good anchors for the natural pose of these limbs. Okay. So let me just position these a little bit closer. And what I'm going to do is use the direct space state raycasting functionality in order to say, okay, starting from the location of one of these points and then going up, the start of the raycast is going to be there. And then we're going to use the facing direction of the enemy in order to determine where are we currently moving to. Or I guess we can have we can calculate the direction after we get it back from the navigation agent, and then that's going to tell us, okay, which direction are we going? Well, the direction we're going is going to determine where we're going to shoot the ray. So if we're going forward, then pick a point, go up, shoot a ray by like half a meter forward. And then that's going to be the new location for this node to be in, for this point to be in. Okay. Now, we will have to handle these nodes as top-level nodes. So after I sample their locations, their starting local offsets, we're going to have to set them all as top level. And after we set them as top level, that's when we can proceed with making them be positioned in whatever direction we're walking. Christopher Walken, oh boy, the spider, it's giving me nightmares. I pooped my pants. Okay. Right, so let's go step by step. Now, because I want to see if I can reuse this for other crawlers, we're going to see if we can make these nodes be in an array. So var, okay, so limb handles. We're going to take all of these, place them into an array. Already. Actually, we probably don't want to do this here. We want to have an actual ready function. There we go. So, limb handles is going to contain this array. What do we do with this array? Well, we need to record their local position. So limb handles origins empty array. Okay, so for each handle in this array, we're gonna append the local position. So we do dot position. That tells us the local offset of the limb handles. And then each handle is going to be set as top level. We'll set it to true. Okay. Now that should mean that as soon as we start moving, actually I think the inverse kinematics are not actually enabled. Now is this function set as top level in base node 3D? The shit you are. Oh, Jesus. Okay, cool. That works. I guess the heart attacks are going to begin now. Okay, so there's got to be a function that we need to call in order to start. I guess we just start. Okay, cool. So for each ik in, and then we're just gonna do this. Each ik dot start. All right. Okay, so okay. Cool. Okay. So that works. Next, let's make a function. Func limb physics. I'm gonna pass delta into it. And I'm gonna call limb physics in the physics process. Okay. Now. We know the destination point. We need Hmm. So this is the control point. Okay. We need to know how far is the control, or how far is the limb actually from the control point? Or I suppose no, if the limb is already leaving the control point, that means we've gone too far. So we need to know how far is the control point away from the next location. Okay. So this is where we need to start looping through these control points. Limb handles. Okay. So figure out the ahead location of the control point. Whew, okay, so this is where we're gonna have to use the direct space state again. So we gotta do physics server 3D. Space state, space get direct space state. No, it wants RID here. What was it that we used in the developer panel? Still can't remember it. No, we just do get tree currency and get world space state 3D. We could just get it from the enemy, because the enemy exists in the world space state, so we could just do it this way. Okay, so we can do boop. We need to give it the parameters. Okay, now the starting position of the raycast, we don't need this, is going to be the point, the global position of the enemy plus the point offset. Handle origins, which means we need to know the origin of the index of the origin we're currently looping through. Take each handle, find it within the array. That's going to tell us the index. Using that index, we can get the offset of this handle before we made a top level right here. We've recorded the local positions of each of the handles. So those positions are in the same order that they are in the global, that they are in the list of these handles. Okay. Need a variable. Now this is the starting point. We're going to add vector 3, 0, 1, 0. So this will, I think this will lift it. No, I think we need to subtract to lift it up. Okay. Now, the destination has to be based while it is top level. Well, we're not actually basing it based off of the location of the handle. We're making it based off of the location of the handle before it was top level. So it's local offset within the parent. Does local position also work? Yes. Yes, local position and global position, I believe, are the same. Well, maybe you should test that. Okay. So take the position of the spider, crawler, add to it local offset. Okay, now here's the problem. The position is global. The position is global, and yet the offset is local. It does not account for the spider's rotation. So that might make it inaccurate. So here's what I can do. I'm going to make a new node. Okay. We're going to call in limb origins. I'm going to take these. We're going to duplicate them. Place them here into limb origins. Now, front left, front mid, back left, back right, front right. So they're in the same order. So now we have limb origins. And these are going to rotate with the enemy. Which means we can bypass the need for limb origins. Let's just set this to be top level. And then when we go here, we're going to simply talk to the limb origins and then get child. And that is going to give us the child global position. And then we lift that up by 1 meter. Now, the destination is going to be similar, except it's a global position. Oh yeah, we don't need this anymore because the points are already in global position. Except we're going to add 1 meter, causing the point to hypothetically go through the ground, and then plus we can run the destination direction. So global position, global position of the enemy will be calculating the direction to the destination point where the enemy is going. And that's going to give us an offset. And the 2 of the raycast is going to be cast in that offset. Okay. And then we call intersect ray. And then collision data is calculated. So now we do if collision data is not empty. Hopefully it's never going to be empty, but you never know. If it's not empty, then we need to do what? We need to take each handle and set the global position to be collision data position. Okay. Now, I expect everything to be jumping at the same time right now. Or not at all, apparently. If valid function direction 2 on base of vector 3, can I convert argument 1 for vector 2 to vector 3? Huh. Okay. Limb origins. Here's a note through D. From vector 2 to vector 3. Oh. Destination point is a vector 3 value. All right. Well, it's a big load on ADA. Well, that is okay. This is why we're here. We're going to add CSG spheres to these origins. Okay. So we can visualize the limb origins. So limb origins are technically there. We do have some debugger errors, which are apparently, yeah, has handle modes. Well, that's a big nothing burger. Okay. Limb handles. Wait a minute. Why are we overriding this? We don't need this. Limb physics. We're looping through the limb handles. Does this actually get to run? It does. It's part of the physics process. Okay. So, one more time. Limb origins. Get the child. Global position. Lift it up. Let me double check something. So if we have, let's say this CSG, if we move it up, it is a positive number. Okay, so that means we have to move it up, and then to drop it down, we have to subtract it. Always forget. Okay. Now, don't you need to activate the IK code? And so I did. Should be right there. I'm pretty sure it should be running. It was running. What isn't running is the raycast calculation, I think. Print DRS calculating. DRS found. Okay, let's double check this. DRS found. Okay, so it is fine. Oh, okay. It's going over stuff. Oh, you know what? I know exactly why this is. It's because we're constantly recalculating it over and over and over and over again. When we should be only calculating it if the distance between the handle origin and the handle itself is longer than, let's say, like half a meter, quarter of a meter. We'll see. We'll dial it in. So if the what? Each handle global position dot distance to this one's global position is less than 0.5. Continue. There we go. So do not rerun the calculation. Can't expect my brain to do any work. Get some rest. Okay. Interesting. Let's place the CSG box in here. We're gonna make it 0.1, 0.1, 0.1. Yeah. There we go. You're at work for another 2 hours still. Oh, okay. I don't think you can afford to let your brain not work for the moment. All right. Good luck. Okay, so interesting. Actually, it is working, isn't it? it does look like the limb is always trying to go towards us. Huh. Okay, let's try increasing. If it's less than 1 meter, we continue. Oh, look at that. It's doing something. You know, it's a start. It's teleporting, but that's kind of what I wanted it to do. Okay, cool. So, in that case, here's what I think we can do. Whenever we are calculating the new location for the bones to go, we're not going to apply it directly to the handle. We're going to make a variable called handle dest, and it's we're going to populate it with values, but we're going to populate it with values in the beginning before we set the nodes to be top level. So we're kind of back to beginning, but we're going to append the global position this time. Global position of the handles so that the legs don't spawn in going in the random direction. And then here, we are going to be comparing what? If the handle itself has the distance to the origin, I think that should be fine. Here, we're going to use the index of the handle that we're currently calculating as the address, and then set it to be equals to this position. Okay, now move the limbs. When we move the limbs, we're going to have to loop through them again, because here we have a little continue operation. Although we could handle the limb moving beforehand, so we only have one for loop. Let's do this here. Move the limbs. So we're going to tell each handle global position dot. We're going to make it interpolate. So global position dot linear interpolate. I think we can do that. Linear interpolate with what? We're going to linear interpolate with the destination it's supposed to be at, which means we have to calculate the index first. And then we're going to calculate it at 0.1. Or we're going to transition to it, interpolate to it by 10%. And because this runs all the time, it technically should smoothly interpolate to the destination. Now this is a function linear interpolate in vector 3, so that's probably because they all just said either interpolate or they said it's lerp now. Lerp everywhere. Okay. Nope. I guess lerp it is. Well, hold on a second. That can't be right. Vector 3. Unless it's interpolate with. There's like 4 different lerp functions. Cross cubic interpolate. Lerp. Yep. So it's lerp. Guess there used to be 4 different lerp functions. Now they all brought it to 1. Okay, there we go. Okay, so that's a start. The next thing we need to do is we need to increase the distance. I think we can do it here. He needs bigger steps, of course. I think that puny little step's gonna do. He also needs to lift his limbs up. Okay. And they're also all moving at the same time. So, you know. They're not supposed to all move at the same time. Leave the distance 1 meter, just move the legs to an even odd fashion. Yeah. We need to do an offset. Update a few legs this loop and a few legs that loop. I know the concept, it's just that loops are instantaneous, so we have to have some sort of a timekeeping operation. I think I know what we can do. We can add a little bit of a timing, operation. So let's do var lim update time. It is going to be an array. We're going to append, for as many handles as we have, we're going to append what? A random time. So we can do os dot, no os, no, they moved it to the time. Class get ticks msec, and we're gonna add a rand I range anywhere between, let's do 300 and 500 milliseconds. Okay, so we're gonna go here, right here. When we're looping, here we go. So if the distance is not at least 2 meters away, okay, if the last lim update time has not passed. So we have lim update time. We're going to access the particular time for a particular lib using the index we've calculated. We're going to check if time get ticks msec minus the last time we've updated it. If it's less than, if it's above 0, I think. No, this would be a larger number. So it has to be, if it's less than 0, continue. Move on to the next limb. But when it does get updated, we're going to populate the current time again. msec plus rand I range between 300 and 500. Okay. Now that should make some limbs be random, and some limbs can do, well, smaller steps and some can do larger steps. That looks like it's doing nothing. Let me also multiply the direction by 2. He's swimming. Precisely. Okay. Time get ticks msec. Current time minus the last time this was updated. If it's less than 0, continue to the next item. Wait. No. Rendai range 300 makes sense. Versatile creature, all terrain. What if I don't check the distance? What if I just check the time? Let me try that. Oh god. Oh god. Oh god. That's way better. So we can pretty much just base it purely on time. If we base it purely on time, he's gonna jiggle those legs even if he's standing still. Okay, so that works. Let's make it go further. I guess we can check either or. Either the distance has reached that point. Oh god, okay. Alright, I think we can make it a little bit longer. Let's see. Let's say between 300 and 1500. So 300 milliseconds or a second and a half. Ooh. You see how jittery it is? So it could update that limb. Yeah, it could update that limb like quickly, or it could wait until it reaches a certain point. So I suppose we should probably make it either or. Nightmare fuel, yeah. Let's give it a slightly longer range. So 500 to 1500. Or I guess Okay. Okay, now right now the points just kind of interpolate to the destination. Oh god. Oh god. The limbs actually point in the direction that it's going. Cool. I mean, that's kind of the benefit of making it an independent system. But now we need to make the limbs rise up and fall down. And I think we can do that right here when we interpolate its location. I think what we can do, we can determine the distance between the limb right now and the destination, and then turn that into a scalar value. Turn that into a scalar value, and after we turn that into a scalar value between 0 and 1, we can use a curve, give the curve a up and down motion, and then sample where along that curve we are, and then that will allow us to use a curve to control the general up and down motion. Okay. Now, if that's the case, we need to make a record of the old position and the new position. Because I think doing it from the current position might not be... might not be so good. You need to make a record of the old position. So at the point we calculate the new position, we make a record of the old position. Huh. You can also use the scalar value just to lift up with sine function. Yeah, but the sine function goes... Oh, yeah. Yeah, but the sine function doesn't have as much control. It would work. I kind of want to try the curve way. Okay. Now. We need to know from where the limb is coming and where the limb is going. So let's make limb update, limb destination, and then let's make var limb old position. And let's say limb destination, limb old position is going to be the same. Okay. Cool. So we're going to say handle old position. We're going to use IDX. And then we're going to record what the destination value is. I suppose that's fine. Or I guess we could just record the global position of the actual handle. So old position recorded. Now, let's do var scalar. Let's do limb scalar distance. We're going to take the old position and then calculate distance to the destination. This gives us the maximum value. Next, we will take the handle, global position, and we calculate the distance of the handle itself to the destination. And then it is going to be the division between the two that gives us the scalar value. Now, I'm going to try something. I'm going to try the sine function first. Each handle dot, I guess, but if we do that, it's not going to be, I guess we can try this. So we do global position dot y plus sine, and then give it the scalar value, and then we need to divide this by pi, I believe. Plus goes up, yes. Plus equals in that case. Could rotate it, tilt slightly. That's the next step, because I don't want the body to just stand there like a log. Okay, now we have a problem. Not existent function, distance to on base array. Handle old position, IDX. Okay. Beautiful. Interesting. It's shy. I wanted to show a magic trick. Okay, let me double check this. Okay, so it's here. And as soon as we add this, it gets Borky. I guess it's because we're just constantly adding it. Yeah, okay. Hmm. Hmm. Let me try just adding the scalar value. Distance between alt position, handle alt position, and destination. That's the maximum distance. And then this, each handle goal position distance to destination. How far it has come. Okay. I'm just going to try this. Well, I mean, those points are just standing still. Hmm. Okay, well, this is wild. Global position on the y-axis. Maybe this limb scalar is just ginormous. Let me double check what this is. Not a number. Excuse me? What is this, JavaScript? What the shit? Each handle. Global position. Distance to handle destination. IDX. Maybe that's not a number? I believe when we get the collision data, we should have gotten the vector 2, unless we got a string. If it divides by 0, it means that this is all integers. But distance 2 usually gives us a string, though, a float. Okay, let's try this. Nope. I'm also not seeing the recalc. Oh, there we go. Position. Alt position. It is an array. In the ready function, we immediately populate it with something. Okay, time to print these two values. Maybe we requested global position too much. We need to send more money to unlock more requests. Not a number, not a number. Huh. Is each handle a valid value? Oh, actually, hold on. We're getting debugger errors. We can take a look at there. Ugh, always look at that last. Okay, the axis vector 3 must be normalized. What? Set axis angle? What are you talking about? Set instance transform. Set axis angle? Where the shit are you? What? Okay, hold on a sec. Just gonna comment that out for a sec. And now it's not complaining about it. And we are getting valid values. So as soon as I try to talk to the each handle global position on the y-axis, which is just a single value, it starts complaining. Also, that is a huge scalar value. Hold on, that's not a scalar value, is it? Yeah, what the heck? That is not at all what it should look like. Okay. So, let's return this to non-floats, or non-converted. Let's take a look at this. Yeah, so it's all like giant numbers. Hmm. 40. Oh, I'm an idiot. I'm printing the IDX in the beginning. Shit. Why is it 10? And then 20, and then 30, and then 40. Ugh. Okay. There we go. That makes sense. Okay, so the float value is there. It works. It is correct. So it really bugs it out when we do this. Global position, each handle, global position.y, and we add this value to it. Really hates it. Okay, now maybe it's because we're lerping it and then also trying to set it. Vector 3, x, y, z. Yeah, no. Vector theme must be normalized. There's no point in normalizing it, though. Okay, what if we do each handle dot position on the y plus equals just the scalar value. Nope. Not a number. Okay. Man. This is actually some weird stuff. What if we do... Vector 3, 0, limb distance 0, normalized. Maybe the float is just too large. Okay. Float and vector 3 plus. Oh, right. Nope. Of course, as soon as I get rid of this line, it is going to work. Okay, I'll Google this after. Yeah. Okay, fair enough. Not y. Plus equals, so we're just gonna do this. We can cause the error. Let's take a look at this. Let's take a look at what's up. Each handle that position. Right. The axis vector 3 must be normalized. You can't normalize 0, 0, 0 vector. It needs to have some kind of direction to be normalized. Now we do have technically a place. When we reach the value. Interesting. What else? Linear interpolation works, but it doesn't give quite the same effect. Linear interpolate. Been using slurp. Global transform on the marker slurp. So I guess we can't use lerp on it. Okay. What if instead of linear interpolation, we're gonna do this. The position is gonna smoothly transition to the destination minus the current position divided by 5. Nope. But I am sure that if I disable this, it will actually work. Yeah. Okay. So, what the heck? Okay, so what if I say this plus vector 3, let's do 0, 0, 0. So we're literally adding nothing. Watch it break. Nope, okay. So what if we do 1? I swear, it's gotta be the float value that we're producing is just too high for a vector. Oh, okay, well that is expected. Okay, so we need to reduce this number. Because as soon as I put it in here, it's not going to work. Yeah, okay. So, I think there's a function for it. Godot float, what is it? Trim float. Rounding floats. Returns multiple of step snapped. Removes multiple of step that is closer to x. This can also be used to round a floating point number to an arbitrary number of decimals. That makes sense. So snapped. Uh-huh. Okay. So I think this will work. I'm going to keep this. Plus equals snapped limb distance to the nearest 0.01. Nope. Nope. And if I comment this out, multiply by delta. Multiply what by delta? The 5? The scalar. I don't know if that's gonna reduce the number of points, but also that didn't work. Yeah. It doesn't like the value. It just doesn't like the value. Okay. I'm gonna comment this out. And let's try snapped. This is the value we're snapping. 0.01 is the range of numbers or the resolution. Okay. Oh. Oh yeah, we're not adding it. But that does look like the correct number. Of course, as soon as we add it here, it doesn't work. What the hexicles, man? Oh, snapped F. This one returns a variant. This one returns a float. Let me double check that. What if we got to do this? The vector3 value has a constructor to which you're providing a vector3 value. So what if we say that the global position is going to be equals to vector3, which uses global position x, global position y plus lim scalar, and the global position z right. I think that's a little backwards. Okay, right, almost. So it's global position plus vector3, which uses 0.0. Yes, this for the y, and then 0.0 for the z. So this gets added to this, then the whole thing gets converted to a vector3, even though it's already a vector3, but the constructor says it can do it. So let's see. Okay, right. This is honestly really frustrating. Yeah, okay. Instance set transform. I think one of the values on the transform got set with a divide by 0, so it went infinite or something. Okay. Okay. Okay, so we know that this works. Oh. Right, we're not applying it, so it's not complaining about it. None of it is 0. I got no idea. I got absolutely no idea. Lerp function returning unhelpful error messages. Right. For rotation, use lerp angle, but we're not using rotation. Transform somewhere being set to non-finite value. Multiply the lerp speed by delta like so. Lerp speed by delta. Okay, so let's try this. So lerp it to the destination, 0.1 times delta. Have absolutely no idea how that even... Well, that works. So this would be more like 10. Okay. Sure. And then if we add vector 3, 0, lim scalar, and then 0. Nope. Still breaks. Delta times lerp speed. (2023). This issue is caused by invalid data in the multi-mesh buffer. Okay, that's not very helpful. Dividing by 0 in the lerp caused the same error. Are we dividing by 0? Lim scalar disk, but we're adding it. We're not dividing it. Okay, unless... This is actually driving me nuts. It is perfectly fine if we do this. The old position is 0. You've got the divide by 0 problem, which would hypothetically cause the entire for loop to fail, which prevents it from updating this, so it's always perpetually 0. That might be it. So what if I do this? What if I take this for loop, place it over here, and then take this out, let this for loop do its thing independently, and then we do this. Oh, okay. Right, but we brought the code back though. So now we do this. Nope, now it works. And also in the beginning, in the ready function, the old position are the current global positions of all the elements. And there is no divide by... lim scalar dist. It's not a number right in the beginning. I'm gonna get rid of this. Yeah, what the heck? It does start out as not a number. Hmm. The old hand position is the same as new hand position in the very beginning. That could be why. Expected closing bracket. What are you talking about? Oh. Right. Okay, so that's not complaining anymore. And yeah, so the second one gives me dists 0, 0. And then when you lerp between 0 and 0, I guess that just gives you crap. Interesting. Okay. So we could check if the distance between the handle and the destination, or the old position, new position, is more than 0. So it's not complaining about it. Okay. Okay. There we go. So the two distances are here. Cool. So now, if we go in and add vector 3, limb scale dist. Let's see it. I want to see some jiggly limbs. Oh, come on. Oh, I think I see it. I think I see jiggly limbs. Nice. Okay. So that works. It's very snappy, but it works. Mm-hmm. Okay. Nice. So if that's the case, we should now be able to add, instead of doing it here, we might actually have a problem with adding the height. Might have a problem with adding the height, mainly because if we add the height, then the height of the limb is going to influence the distance between the limb and the destination. So if we are using the scalar destination, we have to omit the height, the y-axis. So we have to do each handle, global position, multiply, vector 3. So keep the x, drop the y, keep the z. Okay. And then the distance to handle destination, same concept. Keep the x, drop the y, keep the z, so that both the limb and the destination are on the same plane. And then divided by this, which I think we might have to do the same thing. Keep the x, drop the y, keep the z. So now the y-axis is completely irrelevant. I think so. And then that's only for calculating the distance. So now, if we get a curve, let's get ourselves a curve. Resources, new resource, curve. I think we just need, yes. Okay, so this is crawler limb curve. Walk curve. Okay. Let's do something creepy. Like this. Just so we can actually very clearly see when it works. So Okay, load it up. And then we are going to simply make it interpolate, but each handle, global position on the y-axis will be set. I guess we're going to add to it. Walk curve, bake, sample baked. No. I forget what the function's called. Sample baked offset. Yeah. Okay, there we go. I guess we could just use sample. And the offset is going to be this scalar value. Oh. Okay. So it works. Let me just do this. I guess it needs to be whatever the current position is plus the value. So, yeah, well, that's what we're doing. We're adding to it. So, maybe using the current position of the limb won't work, because the current position of the limb also has to be adjusted. Okay. So, in that case, here's what we can do. We're going to get ourselves a variable, which is going to be, what is it going to be? It's going to be a variable, an array containing 5 float values. They go from 1 to 0. And each float value is going to be the scalar transition that we will be using. Okay. Scalar transition. Before I commit to that. Yeah, I think I have to commit to that. Okay, let's do limb move progression scalar. Append, we're going to do 0.0 into all of them. Actually, let's do 1.0. Okay, so when we calculate the new position, we're going to set the scalar progression, IDX back to 0.0, and it will be the job of this loop to progress it forward. Okay, so we're going to say the limb plus equals, you have to reach 1.0 minus the current value divided by 5. Okay, and then we're not going to be using, in this case, the distance, the scalar distance. We don't need all these print commands. Instead, we're going to be using that value, specifically the scalar value for each limb. Okay. Now, we're going to be setting the global position to be anywhere between the starting position, so we cannot be using the current position of the limb anymore. We have to say go from the old position. So old handle, old position, IDX. From that old position, we're interpolating to the destination, and this is the value that controls how far we interpret. And then here we can add a sampled baked value to the end of it. It has to be a vector 3 value. 0.0, that value, 0.0, close. Limb scalar dist is not declared because we don't want to be using limb scalar dist. We want to be using this scalar value instead. Okay. Oh, boy. Jesus. Yeah, okay, so let's reduce this to like 25. It is working, though. It is working. Okay. So it has this weird shuffling effect to it, which kind of makes sense. This is where we're going to have to dial it in just right. Oh, God. Dude, that's creepy as shit. Okay. What if we do this? Twitchy makes nervous, yeah. Okay, well, I mean, what's going to happen now if we do... Let's say if we do this. So we have this command. Let's print this array so we can double check to see what it looks like. Okay, so they're all going from 0 to 1. See, the only problem is that because they're not basing their movement on the distance of the limb, that makes it not quite right. Okay, now we can see them floating a bit. Actually, no, they're not. That's creepy enough to give you nightmares. Okay, now what if we increase the speed now? What's the speed like? Speed is 2. Okay. Okay. So you see, if it's moving faster, then the limbs have to update faster. And also, I think this is just too slow. You know what? I think it's not that it's just too slow. I think it's because it's a curved motion. So it slows down. Yeah. Yeah, see, it tends to slow down by the time it gets close to the edge. So I think what we're going to do is make it 2 times delta. 2.0 times delta, and we have to clamp it. Clamp between 0.0 and 1.0. Okay. Some of the limbs are really taking forever. Move the handles of the curve to get rid of the easing. Yes, we can do that as well. But that's only up and down easing. Oh, jeez. This thing drove me off the face. Okay. We can do that. Also, we could increase this speed, which makes it traverse to the destination a little bit faster. Ooh. Okay. I think at the speed, higher speeds, the 2 or 1.5 seconds wait time is a little bit much. Slimy meatball, pretty much, yeah. Okay, now that's creepy as shit. But it does prevent the limbs from falling too far behind. Which, actually, this is something that we can... Oh! This is something that we can achieve through distance checking. To make it turn towards us. Yes, that is, of course, the next step. Now, to make it turn, I think this one should be fairly simple. So, you know what's weird is that lerp angle doesn't exist on vector 3s. We have to do something with calculating the angle towards us here. Let's see. Let's say we're going to make a variable var look at destination. Okay. That's because I do want this enemy to be able to like look at us but then creepily crawl into like a different destination. So we're going to go here. We're going to say look at destination will also be player's global position. And then here, what do we want to do? Well, we need to make it rotate. We need to make it rotate. There's two ways that I can do this. You see, rotation, I can rotate the object on the y-axis, but that kind of means that if it's only on the y-axis, you can only rotate left and right, no up and down. But there is technically another way that I can rotate it. So I could make, let's say, what is it, the armature? Not the armature. I could give it a node. Okay, let me try something. I'm gonna make the armature bone look at us. Set bone. Can we make a bone look at something? Nope. We can only have 2D or 3D nodes look at something. I use the global basis t dots something something. Okay. Let's take a look. Set bone rotation. It wants a bone ID. Okay, so this would be the body bone, which I believe would be bone ID 1. Rotation, quaternion. Okay. Global. Global basis. Is that something? Okay, that's only on the one axis. Let me double check that. What the heck? There we go. Returns the transposed dot product between width and z-axis. C transposed. Equivalent to basis.z dot vector 2. Okay. Let me try something simple for now. So I'm going to say us, so I don't need to talk to us. Rotation.z, that y, excuse me, is going to be lerp angle, not on base float. Okay, so we have to use standalone between rotation.y and well, now we need to get it to do global position. We need to rotate it to face the angle. So the way I do it is kind of hacky, but I omit the up and down axis, and I just treat the 3D game as if it's a 2D game from the top-down view. So do global position.x, global position.z, and then angle to point, vector 2, and then we're looking at look at destination dot x dot z, and then the lerp angle will smoothly transition that for us like this. Okay, now you see it's looking at us, but it's reversed. And I think to fix that, we need to flip the two angles. Okay. Let's fix the brackets. Now this solution is as janky as it is functional, but it only gives us one axis of rotation. Okay, that's almost right. It's also creepy as shit. I think we gotta reverse the angle. It's either that or we have to reverse the X and Z axis. Yeah, there we go. And we just need to rotate it by 90 degrees, which is plus pi divided by 2. Okay, there we go. Well, that's creepy enough. Yeah, fun times. Pet him with a shotgun. Okay, I do think we need to also take distance into account, because you can see, especially when he turns, he's got that little stretch happening. So let's see if we can implement the stretch here as well. So if the distance between the handle and the origin okay. So what we're going to do is we're going to allow this to continue. You know what? I think it might be easier if we do this. So if this is less or equals, what was it? So if it's above 0, above or equals to 0, so that means this time has passed, or the distance between the limb current position and the origin has surpassed 2 units, then we are going to recalculate. Okay, it's technically working, except for that one time that it dragged its limb. The right limb is just like, nah, this one's broken. Okay. Oh, that's interesting. Oh, maybe that's why. It's because it like rotates around that limb. Okay. Now, that's not the only thing I want to do. I want to try rotating the main bone. Let's do var body rotation vector 3. We're going to go to the physics process. And then we're going to do skeleton 3D dot set bone rotation. The bone ID is 1. And then rotation is here in quaternion. Okay, quaternion and radians are... What's the difference? Are they even the same unit of measurement? Or do they represent different things? What is it? Degrees, radians, quaternions? Or is quaternions and degrees the same thing? This is where my complete failure of any knowledge of vector math is going to bite me in the butt. Okay, we're going to do body rotation dot x. It's going to be equals to sine I guess I'm gonna try something here. Bar, body, wobble time, 0.0. Body wobble time plus equals 10 times delta. And then I'm just going to feed it here and see what happens. We don't need to declare it. Okay. Invalid type. Big skeleton cannot convert argument 2 from vector 3 to quaternion. Uh-huh. Built-in variant is a 4D data structure that represents rotation in the form of quaternion. Yeah, okay, so it's a third type of whatchamacallit? Third type of unit of measurement. I think it exists to combat gimbal lock, because the first dimension is the weight. If I remember correctly, compared to the basis type, which can store both rotation and scale, quaternion can only store rotation. Just a few more minutes and off home? Sounds good, man. You can do it. Quaternions comprise about 4 floating points, W, X, Y, and Z. Those components are very compact in memory, and because of this, some operations are more efficient and less likely to cause floating point errors. Get angle, get axis, slurp are faster than their basis counterparts. Must be normalized before using for rotation. Uh-huh. Ah, look at that. Looks like we can do quaternion, X, Y, Z, and W. Okay, let me try something. So this is like a whole new thing. Match a signature and needs 4 values. Oh. Okay, well, it's upside down. Okay. Okay. So that's we're getting there. We're definitely getting there. So it does accept axis and angle. Arc from arc 2. And also takes a basis. Okay. Well, anyways, if I multiply this by 0.2, and then on the, so we get y, let's do z. And then we're gonna use cosine here. I think this is gonna produce a very weird wobbly look. Oh god. Come here. So with this method, we can actually make the thing tilt in the direction that it's going. So if it's walking left, it's going to tilt left. Jesus Christ, yep. See, now that we've added body movement, this thing is looking... It literally looks like it's just hobbling towards you. Now, we can add additional animation or additional bones, let's say, to the mouth and eyes. And let's say when this thing gets within a certain region, we can have it open it up. The weight painting's perfect as is. I mean, at faster enough motion, yeah. Like when the body's not stationary, you can't even tell. It looks kind of nasty. Okay. Disturbing as fuck, yeah. Yeah, it's definitely disturbing. Nice. Imagine this thing in the fog. Oh, don't even want to. Okay. Let me try something real quick. I'm not a huge fan of the oscillation being even. I would much rather have it be, have it have a bit more of a effect. But we can do that. We can do that by taking maybe wobble body rotation and then organizing it or building it up here. So body rotation.x is going to be this. Okay. Body rotation.z is going to be cosine. And then building it here. And then this dot z. And then this would be dot y. I guess we can also do dot y. We're going to make it sine, but we're going to multiply it by 0.3. And then we can stack multiple sine waves together. So let's say we'll do sine plus sine at a different time. Okay. And then the whole thing is just going to be like this. Okay. You can kind of see when it falls in and out of oscillation. But I think the more of these we can stack together, the creepier it's going to look. Also, we definitely need to reduce it. 0.3. So we have, oh, okay, we probably shouldn't have two sine waves with the same exact time offset. 1.437. Let's get some odd numbers in here. Jesus. Okay, that's good. Brutal. Yeah, I want to break up the pattern. I think maybe the z-axis rotation is also something we'll have to do. What the shit? What's up? Sir, are you okay? I think it's like, oh, you know what? It's self-colliding. It's self-colliding. We need to add exclusions to its own collision shape. Exclude. think we just do this. Exclude an array of RIDs. Hopefully that will be okay. Oh. You actually need the RIDs. Okay. So it probably references something else right now. So get RID. So self isn't RID then. Interesting. Do you see how it crawled over the crawled over these? Like, it's actually reactive to it. Oh, it's still bugging. Interesting. Okay, now what if we add the twitchiness? Except if we do that, we're gonna need to increase the duration. We can set up radius so the legs won't face the objects. Yes, yes. Agent. Oh. Shit. I think we need to increase the drop so it actually reaches the ground. Yes, we definitely need to decrease the speed. Yeah, progression scalar, so it's gonna be like 2.0 times delta. Looks like he's about to stab you. What the shit? I feel like for visualization's sake, we need to show where the destination points are. It's only the three of us. Yeah. Sure. Come to Papa. You can do it. Interesting. I suppose the problem is because when we make a record of it, we make a record of the handles. Of the old handles. Maybe, instead of making a record of the old handles, because the handle could be in midair because of its up and down motion, maybe we'll just make a handle of the old position. Of the position before we write the new position into it. I think that might be better. Oh, okay. Yeah, the wobble isn't really great. pretty much done for today. Just wanted to play around with it. Okay, I think the wobble is way too strong. What happens when we do this? Ooh. 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 Easy there, Sonic. Okay. Yeah. I think maybe right there. You'll go up and down. It makes more sense for it to do that during its travel, though. Because otherwise the limb will look like they're sliding. Yeah, so I guess we'll just keep it this way. Hold on a second. Wait a minute. Wait a minute. When we set it to 0.0, which means it goes back to 0, the beginning. So I suppose the problem is that the time is hitting first. Okay, so maybe we should do this. If the distance is larger than 2, we're going to omit the time for just a second. But first, the distance has to be at least... okay. We don't want to use the distance. I think I know what's up. So we're going to do this. We have to wait for the limb to actually reach the end. So if less than 0.05, then we're going to try this. So this is the progression of the limb going forward. Has to have reached, 0.05 is almost in the beginning. We have to be above 0.95. Which again, this doesn't guarantee that it's going to look good. Oh yeah, because all of them are now moving at the same time. They're all surpassing that distance at once. So then we have to implement this. If this time is less than 0, continue. Okay. I mean, right now I'm kind of scraping the bottom of the barrel of possible solutions. Okay. And this is where we might want to increase the speed. And then probably also increase the wobble a little bit more. That looks pretty good. I feel like I should still employ this condition. So if this is within the 2 meters, then we can consider bypassing it if the time hasn't reached 0. The update time. There we go. But as soon as we start turning around, I think I want to slow it down, actually. Slow down the rotation, that is, which is done here. There we go. So this is going to be 0.02. So that should make it rotate a lot slower. Okay, what if I make this oscillation slower? All right, let's hide all of these debugger shapes. I feel like some of them end up moving a little bit too quickly, or almost at the same time. So we could say that every odd and every even is going to have a different timing. Let me just double check this. It's not really random. Let's do plus 0 if idx, or I guess plus 200 if idx, we're going to modulus it with 2, and if that is equals to 0, else we're going to do 400. Oh, now it's alternating. But it doesn't seem to be moving back. So it's probably going to have to be like 400 and 800. Okay, but now some limbs are moving at almost synchronized rate. So let's do 400 plus either 400 or 800. So there's a minimum. Okay, the last two limbs are not really doing good. So maybe we can do 400 plus plus another 400 times IDX modulus 3. So every third limb. See, the limb doesn't spend long enough on the ground to look like it's moving. And also, right now, all the limbs are just like one after another. You can see a rhythmical motion to them, which is not really good. Ugh. Well, now he's stuck. Come on, buddy. Okay. Let's omit this. Beautiful. I know, right? It's a face only a mother could put up for adoption. Let's see. Let's make it distance-based. Because I really feel like it should be distance-based. Like, spiders don't time their legs. They're just, if the leg is too far away, they move it ahead. So if the leg oh yeah, if we do it distance based, it's gonna cause all the legs to move at once. Interesting. Maybe I'm gonna leave this little problem for another day. I'm gonna call it a day. 3 hours, 3.5 hours actually. Think we've done enough damage here. Long day, productive. Yeah, I'd say we got some pretty good stuff going on here. Now I'm gonna try to make sure that the system that we've created here can be propagated to the other two versions of the crawler. Okay. What's happening here? Unexpected indentation. All right. You know, come to think of it, I think I might have an idea of how we can make this work. You see, we do give the limb a random amount of time before it resets itself. What if we say 50% of the time that it is given is going to be used for traversal of the limb, and then the remainder just waits in that position. So in that case, if we give it 1 second, then half a second is going to be spent moving the limb. If we give it 1/4 of a second, then half of that quarter, an eighth, is going to be used to move the limb. So that way, it's not just like the movement isn't just an arbitrary number going up. The movement is based on how much time we've given it. Now, I think that should be pretty easy to do. Where do we advance it? We advance it right here. So what if we say that the advancement is the current amount of time divided by the amount of time it is given. And then we clamp, of course. But this has to be half of that time. So we gotta... I mean, right now I think it's just going to be progressing based on the entire time. Oh, God. Oh, right. We don't add. We make it equals. Okay, now that's instantaneous. Interesting. Now why is it teleporting? Probably because this difference is not the same. You're overriding it in the second line. Yeah, but I'm overriding it by clamping it between 0 and 1. I would imagine that if you take the current time and then dividing it by the maximum time, which is current time plus a random number between 400 and 900, then this is going to be larger for at least a short period of time. If we take the current time divided by this time, this should be larger. Interesting. Okay. Hopefully this quick experiment isn't going to turn into another 2-hour endeavor. Oh. Okay, let's see here. That's actually... So it's always hovering around this. What is his texture gonna look like? Gnarly and nasty. Probably gonna have glowy eyes. Let me double check this. Make it more organic. Yeah, that's kind of the point. Okay. So 11.961 versus a number that is clearly larger than that. Maybe they glow when they find you. Yeah. Yeah. That's actually good user feedback. indicator, player feedback. Once they stop glowing, and that's the creepy part, once they start glowing, you don't see it. Yeah, this is weird. Oh, I think, yeah, I think I understand why. It's because this does not start from 0. Yeah, so there's no way for it to actually start from 0. I think I know what I need to do. I need to make a record time. Lim update time. Lim update. Technically, lim update time is the time I'm looking to record. So let's say lim update delay. And then this is lim update time. So it's the time when the lim was updated, which is this, but without the extra random range. There we go. Out of gas. Have a good night. Sounds good. I'm gonna call it in a moment as well. Okay. So we need to do this, the current time, minus the time it was recorded, divided by this. I think that's it. Oh, evaluate index 0. Right, we have to populate at least like starting values into it. We're gonna append the current time. Sure. Okay. Well, I mean, technically it works. It does reach the 1 second, or the 1.0. So in that case, to update it, we don't wait for the time. Well, actually, we kind of do, don't we? Okay. You know what? I think that's fine. I gotta call it a day. Cool. Well, we got some stuff working. I think we're gonna continue this in the next one. And cool. Thanks everybody for watching. Appreciate the company.